All right. Thank you all for coming. We'll begin with a acknowledgement of country. We acknowledge the traditional custodians of the Macquarie University land, the Wallumattagal clan of the Darug Nation, whose cultures and customs have nurtured and continue to nurture this land since time immemorial. We pay our respects to elders past, present, and future. Our speaker for this month is Markus Pantsar. Markus specializes in the philosophy of mathematics and philosophy of artificial intelligence. He received his PhD in 2009 at the University of Helsinki and is currently working as a guest professor at the RWTH University in Aachen, Germany. He's the author of the book Numerical Cognition and the Epistemology of Arithmetic by Cambridge University Press, 2004. Please welcome Markus.
Thanks, Oda, and thanks for the invitation. I'm happy to be here. And indeed, in the talk today, I'll be putting together my two research interests, so philosophy of mathematics and philosophy of AI. And when it comes to AI, of course, there's so many different topics that one might be interested in when it comes to mathematics. I'm interested in all those topics in one way or another, but today I want to focus on epistemology and talk about mathematical reasoning. So there are some successes, as I will soon tell you, in AI mathematics from the last year or two that have been quite surprising. And we're starting to reach the point where AI tools will be very important in mathematics, much faster than we expected. So we need to figure out what is all this going to mean in terms of knowledge production. How can we trust these AI systems? And that's why I focus on reasoning. One way or another, when we are dealing with mathematics, we want to know that we are basing our mathematical knowledge on valid reasoning. And how to get knowledge of that, how to get knowledge with AI tools, those are the big issues for today's talk. Right. First, I'll talk about reasoning in AI systems as a general aim. So a lot of what I'll be talking about, I feel at least, is generalizable to all kinds of knowledge production. Mathematics is used more as a case study than a distinct field. So first, I'll talk about reasoning in AI systems in a general way. And it's very well known how LLM-based AI systems fail in reasoning. This was a big issue in philosophy, it was a big issue in tech, journalism, it was even a big issue in mainstream journalism. For example, the infamous strawberry case. The first AI models like ChatGPT was not able to calculate how many letters there are in the word strawberry. This became something of a joke to show these AI systems are terrible. It will always say that there are two R's. For some reason, that was how it failed. It couldn't calculate simple averages. And this was not just ChatGPT, also Claude, Gemini. They were notoriously bad in these tasks. And it became an embarrassment. You have these insanely expensive systems and they fail in such simple tasks. So it became a big research point for companies like OpenAI, Google DeepMind, Anthropic, but it also became an important marketing point. Up to the point where we are now, where models like GPT-5 and new versions of Claude are not called large language models anymore. They're officially called reasoning models or large reasoning models by these companies. Instead of LLMs, they like to talk about LRMs. But fundamentally, nothing really changed in how this model is trained. What did change is that before it produces the output based on your prompt, it does more iteration. And it's got a better system for reinforcement learning based on outputs that we enter into these prompts. And that's what it is. But it's sold as something very different. It's sold as a big leap in the ability of these systems, making them human-like in their reasoning. I'll just quote here from OpenAI's marketing speech of GPT-5. Reasoning models like GPT-5 are LLMs trained with reinforcement learning to perform reasoning. reasoning models think before they answer, producing a long internal chain of thought before responding to the user. Now, there's quite a lot that's interesting in there. First of all, I mentioned that reasoning became a big marketing point, and this clearly is happening here. They are marketing this system as being better because it can reason. But what does it mean? What are they saying here? Saying stuff like long internal chains of thought or that they think, quite frankly, means nothing. It's just picking up some cognitive terminology to make the system appear more human-like in its functioning. That's all it is. It's really about more iteration and reinforcement learning, something that was already in the previous models. It's just improved. So there's nothing in the designs of so-called LRMs that suggest any qualitative leap, that now, instead of these old models that were just statistical models, right, incapable of reasoning, now these new models are capable of reasoning. That's just how it is, based on the knowledge we have of these models. But clearly there is a quantitative development. When we move from GPT-3 to GPT-5, for example, whatever these new features or improved features do, it has been successful. It does make the system much better in many types of reasoning tasks. And I think that's something worth considering. How should we consider it? Well, the big question, well, it now solves reasoning tasks better, but is it reasoning? And I think we can approach this from different directions. What does all this mean in terms of the AI system's capacity to reason is the big question. And the AI industry speak, this is all the companies, but it's unfortunately also a significant part of the tech journalism. They're happy to make a direct connection. This AI system is performing better, significantly better in reasoning tasks. Therefore, we can say that it's reasoning. But of course, that's a very dubious connection to make. And this can be criticized from two directions. I'll be focusing on both of these. First, we can say that yes, the LRMs are getting better in reasoning tasks, but they still have major weaknesses that might be potentially irredeemable, but there's tasks that it can't solve. Second, we can have the approach that yes, they are getting better in reasoning tasks, but what are called reasoning tasks can actually be solved without reasoning. These are two different lines of critique that both have received a significant attention in the last couple of years. The first line of critique that I say is called here, it's not reasoning because it keeps failing. That's about the extension of what we call reasoning and what the AI capacity in reasoning tasks is. This is something that in the industry, people are very much focused on. There's a famous paper from last year, The Illusion of Thinking, from some Apple researchers. This made rounds, became sort of viral within technological and philosophy of AI circles, where they try to show that there are tasks like the game Tower of Hanoi, which is too complex for these systems to solve reliably, but human children can actually solve this game. And they had other examples like that. Based on problem complexity, they show that there are limitations to what these models can do. So there's a difference in the extension. Humans can solve some reasoning tasks, AIs cannot. But actually, we don't need sophisticated studies like that. It's a sort of a party trick that I have. In 2 minutes, I can find a reasoning error in outputs of these models. It's becoming harder, but I can still do it, I promise. I just use an old example here for convenience and also because it relates very well to the reasoning marketing speech that these companies have. So OpenAI, as I said, was very embarrassed by the strawberry example, and it released a new model called Strawberry AI, which was advertised as being able to handle complex mathematical problems. And I tested it with the prompt, rank all the European countries in terms of population. I checked this, by the way, in January. It's still with this model was not fixed because I haven't published this, but whenever something is published, they fix it very quickly, right? But this is the result that it came up with. So it's nonsense. This is clearly not an order. I mean, the populations are right. That part is somehow correct. So there's a consistent basis for that, but the order is just not there. Now, as I mentioned, finding such failures, it's sort of a cat and mouse game. There's tons of people. It's a whole Reddit phenomenon where people find these examples and then they're fixed very soon. But this sort of patchwork improvement can't be thought of making the system better at reasoning. So that we can find these examples still, and we can find it remarkably easily, is a pretty good argument for them not actually being able to reason. That they fail so badly is very significant. But what actually is the significance? I think that's something worth thinking about, because it can't be the fact that the AI systems fail in reasoning tasks. It has to be the way they fail in the task. Cameron Buckner has pointed out very astutely, in my opinion, that AI critics sometimes have double standards. Whenever they see AI errors, they see that as evidence of lack of particular ability, like reasoning. But human errors are considered to be characteristic of that ability, features instead of bugs. Good example is the Watson selection task. Every psychology student learns about this during the first year. So when they're presented with 4 cards like that and asked which cards you need to turn over to test the rule that every card with an even number has a blue back, almost all students fail. And not just students. Incredibly, also logicians and people who are supposed to understand rules like that typically fail. Generally, 90% of human subjects fail. What they do, of course, is that they start turning cards based on these intuitive connections that they get. By the way, how does one solve this? Which cards are needed to turn around to test this rule? Well, the rule is every card with an even number has a blue back. So 8 being an even number cannot have a red back. So you need to turn over 8. And of course, blue card can't have an odd, sorry, I'm getting confused myself. But you need to turn over also the red card because you can't have an even number with a red back. But most people say blue and 3 because they want confirmation rather than looking for counterexamples of the rules. Anyway, I want to spend more time on this, but this is a good example how human reasoning actually in some simple tasks fails most of the time. We consider that to be a feature of human reasoning. How can we think differently in the case of AI? Failure itself can't be the problem. This is my point here. We are otherwise vulnerable to a very problematic position, which is that AI system could be equivalent to or even better than majority of humans in performance in reasoning tasks, but we only attribute reasoning capacity to the humans and not to the AI. Then the question is, what do we need from the AI in terms of performance in these sort of tasks to accept that they might be reasoning? I'll return to this later. But the point here is not that it's just a failure, it's how they fail. So the population ranking task that I had above is something different. The AI system does fail, yes, and humans can fail in such tasks. But there's an interesting difference, I believe, in how they fail. A human might be careless, they might make a mistake. That typically happens with humans. We sort of strive for precision, but we are always lacking the necessary attention. But computers don't have such problems. From computer, unlike from humans, we should expect error-free performance if it correctly identifies the principle for solving the problem. Basically, if it is able to compare 2 numbers and put them in order. It should be error-free every time, right? That's why we trust calculators and computers and so on. So I think it's highly probable, based on this insight, that Strawberry AI's performance here is not about some kind of human type error, lack of attention, something like that. Rather, it's very likely that it never identified the principle for solving the problem. Whatever the principle may be, it just didn't identify the correct principle. And of course it didn't. We off the record, we know that because it works on statistical connections. The connections that it used for this list ranking come from somewhere else. They don't come from a list of countries. They come from some other rankings that they find. And that's how this sort of silly error ends up being in the list. And that's a problem because the system, because of this functioning principle that they have, is likely to fail in unpredictable ways. Humans fail a lot, but typically human failures are something we can predict. AI failures are something different in this sense. So this is the question of extension. Whether AI systems are able to reason or solve reasoning tasks in a way that's comparable to humans in terms of the extension. How many tasks, what kind of tasks it can solve. But ultimately, this question is also about the intention of reasoning. Even if we had a system that can solve all the tasks that humans can in human-like way, be predictable in that sense, we still would be interested in the question whether it is actually doing reasoning or whether it is solving them by another means. Because reasoning tasks, and I know that it's a bit frustrating that I haven't defined reasoning or reasoning tasks. I will come to that very soon. Reasoning tasks can be solved in different ways. A successful solution does not indicate that a proper reasoning procedure has been applied. Consider mathematical tasks, my first entry into mathematics here. Think of your educational background in mathematics. We, I assume, accept that mathematical tasks, if anything, demands reasoning. And in educational contexts, we aim to present tasks that require reasoning. We want to measure progress, ability in terms of reasoning tasks. That's what mathematical education is fundamentally based on. But students find shortcuts. Instead of them being able to solve the problem in the way that we want them to, they find some heuristics. That's a very typical strategy. I used to teach mathematics in high school. I know about this. They rather go through the trouble of finding these heuristics, how they can just fill values into some sort of scheme, than understand what's actually going and try to solve it by reasoning. Of course, the student would be still doing some kind of reasoning. I mean, it's all about reasoning. But in terms of the task and its desired solution, there might be a misalignment. This happens with humans. I'm sure it happens with AI. And that's a concern for us. Because AI systems, yes, both generally and in mathematics, they have become much better in solving such tasks. But in what way are they doing that? Are they reasoning in any way that we would align with human reasoning? Or do they solve the problems based on something comparable to the heuristic procedure by another kind of process, detecting patterns in the training data that contain a lot of similar problems and their solutions? Now that's where I want to now finally enter the question, well, what is reasoning? I won't go too deep into the philosophical details here, but of course philosophers have been differentiating among different types of reasoning. The classical three-part distinction nowadays is deductive, inductive, and abductive reasoning. But technology companies, when they write about reasoning, it's usually much more inclusive than that. Here I have IBM's list, which distinguishes between abductive, agentic, analogical, common sense, deductive, fuzzy, inductive, neurosymbolic, probabilistic, spatial, temporal reasoning. Well, fair enough, we can fruitfully describe all such reasoning procedures, but what exactly is it about them that makes it reasoning rather than other form of information processing? And in philosophy, there's a long tradition from Aristotle to Davidson, I guess was the final nail in the coffin at the time, at least, to the idea that there might be something like non-linguistic reasoning. Davidson takes reasoning to be only a linguistic phenomena based on rules that we understand. There's another tradition, sort of a more recent but related tradition, which take reasoning to be about mental notions like attitudes, like Broom and McHugh and Wainwright, or mental states like Wedgwood writes. And AI skeptical philosophers welcome these kind of traditions, I'm sure. An AI skeptical philosopher, when it comes to this latter kind of approach, can easily spell why AI systems can't be reasoning, because it's very unlikely that AI systems possess something like conscious attitudes and mental states. That's a very common AI skeptical argument. Of course, there are people who nowadays claim, at least carefully, that AI systems might be developing something like consciousness, but they are still very much in the minority. A large language model skeptical philosopher in particular, and I'll come soon to why here I focus on LLMs, might welcome the former kind of approach, the Aristotle-Davidson approach, since reasoning is based on applying rules and applying them in some way consciously, knowingly. What LLMs are doing can't count as reasoning. This is connected to probably the most influential recent paper on reasoning by Boghossian from 2014. But I'm not satisfied with either of these AI skeptical arguments, because it seems to include what I've called previously meat chauvinism, that reasoning is limited to biological systems, or intelligence is limited to biological systems, metabolizing systems, instead of being about the structural characteristics of information processing, regardless of what the system is made of. And I don't want to impose such wholesale restrictions. It's sort of too easy as well. AI systems can never reason if we just say that they can never have mental states or conscious attitudes, or we can say that LLM-based systems can never reason if they're not knowingly applying rules of reasoning. So that can't be the end of it. What if the systems 50 years from now are completely different? Can we still use the same argument? In fact, I'm feeling that we are already running out of power with this argument. 5 years ago, it was a better argument than it is now. But that can't quite make sense if we are talking about fundamental properties of these systems. So instead of that, I want to argue here that we should figure out what the AI systems are actually doing in their processing. I know that that's a big problem. The famous black box problem tells us that the complexity of these systems is just prohibitive. We can't ever know what the algorithm behind particular prompt output connection is. But nevertheless, I do think that we can have some knowledge about the processing. We can't reach the algorithmic level, but we can know something about. And then this knowledge we should evaluate in terms of its alignment, its similarity to human reasoning processes. This is the way to go instead of these sort of wholesale denials. And now I move to mathematical AI. So, of course, it's important to realize that mathematics and AI have been connected for a long time, but in the first wave of this current AI boom, LLM-based AI boom, mathematical applications initially didn't play a major role. In fact, they were the embarrassment. These systems were very bad at mathematics, which historically sounded a bit weird because mathematics was one of the success stories right from the beginning. Take the logic theorist by Newell, Simon, and Shaw from 1957, often called the first AI program, definitely falsely, by the way. There was AI programs playing checkers before that. If it can prove theorems, other program can play checkers. What's the difference? Why is one AI and one not? I don't get it. But it's still called AI program often, the first AI program often in the literature, and it proved theorems of mathematics. In particular, it proved Principia Mathematica theorems of Whitehead and Russell. And they were very excited, and so were mathematicians, because now we had something that clearly demanded human cognitive ability previously, and now it can be conducted by a mechanical machine. So Simon famously said, by the way, that he solved the mind-body problem with this program, and he was not kidding either. But it was still a big achievement, even though it's crazy to say that it was an intelligent system. It was just a simple search function mechanism. But that started a venerable tradition of mathematics and AI being connected. And there are well-known cases where mathematical proofs have been conducted with the help of computer, like the four-color theorem, which states that any map can be colored with only 4 colors so that no 2 adjacent regions have the same color, or Kepler's conjecture, which are cases where computers made the proof possible. Why did they make the proof possible? It was through sheer computational power. So in mathematics, there's a proof method called exhaustion, which means that we just calculate a large number of cases one by one and show that the general theorem holds. Of course, usually this works only for finite collections, and usually in mathematics, we are not interested in finite collections. The key here in four-color theorem, for example, was that we could show a lower limit and an upper limit, and now we only had a finite amount of cases. We put the computer, or they put the computer to crunch the numbers. It was confirmed, theorem proved. But as far as mathematical proofs go, mathematicians hate proofs like that. They're considered to be inelegant or uninformative or plain unintelligent, because they don't show any connection why the theorem is true. It just shows that we can go through all the cases and that's it. Now that used to be the only way we could contribute to mathematical proofs with computers. But we are very close to this being changed. Last year, both OpenAI and Google DeepMind reported something quite remarkable, which was that their systems had reached gold medal level in the International Mathematical Olympiad. This was widely reported in tech journalism, in popular science magazines, but also in New York Times and Washington Post, in Guardian. All the major newspapers reported this rather visibly as a new benchmark for generative AI systems. Now, AI systems are as good as the best secondary school mathematicians in the world. So it's a remarkable achievement. We should not downplay the importance of this. But it's still dealing with existing mathematics. And it might still be dealing with mathematics in this sort of heuristic way. There's only so many problems you can have for such an exam or such a competition test, and it's quite likely that they repeat patterns. In fact, the earlier systems already reached silver medal levels, which were not supposed to be doing any reasoning at all. So that makes this a bit iffy. Was this such a great achievement after all? Well, if there's any doubts, these doubts might be disappearing soon, because there have been reports that AI systems have been used successfully in research level mathematics. There have even been voices that very soon we'll have the first cases of AI systems being used for solving important unsolved problems, like Navier-Stokes existence. It's a millennium problem, so if you go through these problems, it's basically the most important unsolved problems in mathematics. You get $1 million for solving one problem. It shows the status that we have for these problems. And there's reports that soon we'll have a solution to that. My hunch is that it's now being reviewed, and that's why we're still waiting for the confirmation, but they couldn't wait, and they already approached some journalism, so this made also newspaper articles. Whether this happens or not, I think we're very close to that happening with some problem. And if AI systems can perform on such high level, the question is, can we still contest that they are reasoning? If they can solve unsolved important research level mathematical problems. Well, how do we deal with this problem? My topic is towards an epistemology of artificial mathematical reasoning. Well, how do we get an epistemology of these sort of problems? And I propose a couple of directions here. Because in this respect, the mathematical systems of OpenAI and Google DeepMind are very different. And it's something that's relevant. I want to pursue this a bit more. Because OpenAI system, which is just ChatGPT, really is based on a large reasoning model. It's just a large language model applying reinforcement learning. So it's basically your run-of-the-mill stochastic parrot deep down, even though it's a wonderfully complex, powerful system. But Google DeepMind systems, AlphaProof and more recently AlphaEvolve, which is supposed to be the system that's proving these new theorems, have both those elements, but they have an important difference. The proposed proof steps, so steps in the solution of the problem, are fed into a rule-based theorem prover software, namely Lean, which is something that mathematicians use quite often to check the formal validity of their proofs. So we get what Gary Marcus calls neuro-symbolic AI. So there's the neural part in the large language model, and there's the symbolic part in the rule-based theorem prover Lean. And I propose that this makes an important difference, because we know that there's a deductively valid process, because we know how Lean is programmed. We know that there's at least some deductively valid process applied when AlphaProof or AlphaEvolve solves a mathematical problem. In case of ChatGPT, we don't know that. Maybe it's able to bootstrap these logical principles from the statistical data, but we don't know. So even though these systems might be equivalent in terms of the extension, what kind of mathematical problems they can solve, I'm not claiming they are, but even if they were, there is difference in our knowledge about the intention. What we know about the processing of AlphaEvolve, AlphaProof, and what we know about the processing of ChatGPT has an important difference. One, we know to be based on deductively valid processes. The other, we don't know. Might be, but we don't know. This is just to show AlphaProof system. So the idea is that there's a huge training material of informal problems that are turned into formal problems, which are then tested on the system Lean and the reinforcement learning, the AlphaZero system, the very same one that learned to play Go and chess, is then responsible for training the actual ability of the system for mathematical problem solving. Okay. Anyway, now the question is, there are these differences between the systems. What do we make out of that? And I think there are two questions that we need to ask here when it comes to epistemology of AI reasoning. First, we must ask, well, how can we get knowledge of AI reasoning, if any? Second question, how can we get knowledge through AI reasoning, if any, by applying AI reasoning? So question about identifying reasoning, question about applying AI reasoning. And these are separate questions, but I will be arguing that they are actually connected in important ways. For the knowledge of question, we must look both into the extension and the intention. Think about this in terms of the failure in the population ranking task. Everybody agrees that this is evidence that the AI system is not reason, or at least I assume most of us agree. But why is this evidence? Why do we think of this failure as evidence against its reasoning? It's actually not such a simple question to ask, because as we saw, humans also fail often. What exactly was so interesting about this failure? And I'm claiming it's because it shows that it was not robust. Whatever the process is, it was not robust. And I want to explore robustness as the criteria. I take it from technological scientific standards, the ISO standards for definitions of terms like that. I just use their notion of robustness, which means ability of a system to maintain its level of performance under a variety of circumstances. I take this as one identifiable characteristic of reasoning when we want to move toward epistemology of AI artificial mathematical reasoning in the knowledge of part. Notably, robustness is not about being error-free, which reliability, which is the standard word used by philosophers of AI here, is defined as. Because I don't think reasoning can be connected to being error-free. What I do think it can be connected to do is have this sufficiently high level of performance when the circumstances change. So if we have a system that can solve mathematical problems and get the gold medal in the International Mathematical Olympiad, but it can't rank population correctly, this is not a robust system. It's specified to some circumstances, whereas it should have high level of performance across a wide variety of circumstances. And that's the difference. Human reasoning is robust like that. It's much more steady in different circumstances. So I argue this is a key characteristic of human reasoning that we can also apply for identifying reasoning in AI systems. That's the knowledge of question, and the knowledge through question may be treated independently of the knowledge of question, but it can also be connected to it. It can be independent, and I think it should be independent in some context, because we don't need to have this kind of knowledge of in order to pursue questions of knowledge through. Let me explain. So currently people are using AI systems like ChatGPT, AlphaProof, AlphaEvolve, all kinds of systems in knowledge production. This is happening in every single discipline right now. One way or another, we are using these systems. But we don't have the knowledge of reasoning about these systems. We don't have a sufficiently good understanding whether we can call them robust reasoners or not. Yet people are still using them, so we need to be analyzing the knowledge through question, whether knowledge generated with the help of these systems is trustworthy, for example. So we need to have the questions separate, but I also want to connect them, because the knowledge of question, our answers to that, may help us justify the use of AI systems in knowledge production. Just to go to our example, if AlphaEvolve is established to be a more robust reasoner than ChatGPT when it comes to mathematical problems, then it makes sense that we can give it a more autonomous role in mathematical proof generation. Why does this matter? Well, because our normal methods of checking mathematical proofs fail. Mathematical proofs, already human-generated, can be incredibly long. There's a famous proof by a Japanese mathematician that's been under review for 3 years now. It's too long for anybody to check on their own. That would mean dedicating your career, large parts of your career, checking one proof. Of course, nobody can do this. But these AI proofs might be way more complex. They might take decades for humans to check. So somehow we need to establish ways to trust these outputs if we want to use these AI tools in the way that people are envisioning now. So basically what we get, AI-generated proofs checked by AI tools. We can't just trust this process based on this kind of extension-based analysis. We need to have an understanding what these systems are doing. Well, let me conclude by talking about consequences for mathematical practice. So in a paper published last year, I distinguished between two types of mathematical AI systems, mirroring a distinction that already exists, but sort of pointing to the future. So there are interacting theorem provers. This is the most common use of AI tools or computer tools in general in mathematics. So human mathematicians use these tools interactively in their mathematical work. Currently, the most common application is that you write formal proofs, you feed them into this computer system, and it checks whether it's logically valid. That's how the lean system is used mostly nowadays. But with the new AI systems, large language model-based systems, we can generate new conjectures. We can generate original proof ideas, which was not a feature of the old rule-based systems. So in this ITP interactive scenario, things are also changing. We are getting AI generated mathematical content in a way that previously didn't take place. That, I assume, is what's happening with this Navier-Stokes equation, for example. It's a big team of mathematicians, top-level mathematicians working with Google DeepMind, trying to find this proof. We don't know the details because it's still a bit of a secret, but it must be some kind of interactive theorem proving. They're generating parts of proofs, and then the humans are checking them. They're getting ideas how to develop further, but it's an interactive process. This will certainly happen. This will be how mathematics is done in the next decades, for sure. I have no doubts about that. How the roles will play out, that remains to be seen, but future mathematicians will be users of AI systems. I'm quite convinced of that. But what I find very interesting is the scenario where we might have something that I call autonomous automated theorem provers, AATP. Something that would potentially take over all parts of the mathematician's work. The human contribution here would just be reduced to creating a prompt. In a simplified example, we could have a prompt, prove me a new theorem. And it provides as output now a proof. And then that's now new mathematics that didn't exist before. Interestingly, by the way, this scenario has been discussed in the past decades, and the part that we thought would be very difficult is writing it into something that humans can understand, rather than having a long formal derivation. An actual mathematical article would be needed, something like that, of course. But actually, that's the easy part now. With these LLM-based systems, that's the easy part, writing it into something that humans can read, because there's so much training material for that. Now, when we think about consequences to mathematical practice, these scenarios are clearly different, and we need to be prepared for both scenarios. In both cases, AI tools would definitely become an important part of mathematicians' toolbox. But in this latter scenario, and here I connected this to the question of epistemic agency, the epistemic agency of the mathematician would be dramatically altered, because now, instead of being active part of this knowledge production process, you're actually just maybe engineering prompts, or maybe not even engineering prompts, just giving rather simple prompts and still producing new mathematical knowledge. And when we talk about mathematical practice, and we should be talking about this because these changes are happening, we might already be seeing mathematical papers submitted that are AI generated to a large degree without that being acknowledged. We need to know how to deal with this. And I just present here a sort of a selection of important questions for mathematical practice. First of all, who is the author of the work? Mathematics is not just this sort of theoretical construct. Of course, it's used in practice all the time. It's used in technological applications. Our academic publishing has always worked on the foundation that the author is responsible for their work. But if it's an AI system that carries out everything here, then who is responsible for that? The human who has submitted it, but maybe if it's not a human that submits it at all, AI systems are not legally responsible for anything. Why would they be scientifically responsible? So is it the developer of the AI systems? We all know how difficult these questions are when it comes to self-driving cars or other AI applications. I mentioned the second question already. How is the correctness of the work established? There's a system in place that we now have, a peer review system, which works based on dynamic principles. If I submit a mathematics paper, I want to make it as clear as possible for the human readers. And they want to communicate back in a way that helps me develop. And there's this sort of interaction going that aims for all of us to understand the mathematical content. But AI-generated proofs might be something completely different. They might be, first of all, prohibitively long, or they might use forms of communication that are not geared toward human understanding. So how do we trust the outputs, especially in this AATP scenario? The ITP scenario, yes, we have humans still in the process, but what if human involvement in the process is minimal? How do we know that something is now acceptable into the body of knowledge that we have in mathematics? And of course, all this, as in all scientific fields, is related to the question of what does it mean to be a mathematician in the future? What is the required skill set? What is the required knowledge base of a future mathematician? When we educate new mathematicians, what should we teach them? We used to be teaching people calculation techniques before we got the necessary tools to automate that. Is this how mathematics will go also when it comes to theorem proving, that we actually don't develop this skill set of being able to prove theorems autonomously, rather we teach them to be users of this software? Here, the question of epistemic agency is again very relevant. Just how much you know about mathematics if you're mostly basing your knowledge based on AI-generated content. Thank you.
Some time for questions. Anyone? Richard? Just pressing a few questions. Oh, at the moment. Wait for the money. Okay, fine. Thank you. Undrawn.
Okay, thanks very much. That was great. I guess I want to just go back a little bit to the definition of reasoning, because as you probably expect, my suspicion is that certainly ChatGPT, in terms of LLMs, aren't doing reasoning at all. They're doing some very, very hard statistical work, but they're not doing that. The other example you had, the kind of hybrid one, is a more interesting case. But I guess one of the things is that some of the definitions of reasoning, it does make reasoning look like it's just a kind of set of linguistic mental states that you transition between according to a set of defined rules, whether those are defined internally to the brain or mind, or whether they're defined by the broader culture or social environment. We can leave aside, but it does make reasoning, the concept of reasoning, very slim. I just wondered if you'd say something about that, whether you think that we ought to go back and take those definitions of reasoning apart, maybe not by just having a list like IBM does, whatever that is, but of thinking of ways in which reasoning perhaps doesn't have to be just a chain of linguistic states that are, in some sense, the result of rule-based thinking. If you think that there's more to reasoning than that, then would that then loop back into the question of what, and being a bit niche chauvinist for a moment, loop back into the idea of what it takes for humans to be good mathematical reasoners, and how that might change the pessimistic conclusion, which is that, well, you're just going to be a prompt writer or an editor and an interpreter of whatever comes out the other end.
Yeah, that's a good question. So there's so many topics relevant to this. So of course there's this question like on what level would this sort of rule-based activity happen, and people like Fodor and his followers would be happy to say that there's something like a language of thought, and that's already a level where reasoning happens. I know that it's not a very popular view these days, but it's something that still one runs into, and there is then a closer analogy, especially in these hybrid systems, that what's actually going there on the level of the very program that's being run could be seen as this sort of linguistic rule-based activity. So I think that's one approach to take. Another approach to take is that reasoning might be similarity-based. So this is something that Cameron Buckner has argued for, that instead of having these sort of known conscious rules, like Boghossian famously says, Boghossian's idea is that reasoning is about taking, and the idea is that you take the conclusion to be the consequence of the premises, and that's when the reasoning is valid. But you need to have this attitude. Otherwise, it's not reasoning, it's just one form of information process. But yeah, so and previously, based on what Goodman argued against in the 70s, is that, well, similarity can't do this. Similarity is way too context sensitive, way too complex, way too opaque. But of course, things have changed. Nowadays, we have formal models of similarity, like Jardenfors has that, and Tversky had that in psychology. So Buckner has been arguing that maybe there are similarity-based models of reasoning that can actually be, now I'm moving into my terminology, be robust in this sense. So not all reasoning needs to be rule-based, it could be similarity-based. And if there can be such a thing as similarity-based reasoning, then large language models can have that, because they can treat similarity on a scale that's comparable to how human brain can treat similarity, maybe even surpasses that. And that's one way to sort of see how reasoning might emerge from systems that don't have rules for reasoning. Now, do I find that feasible, or do I find that this might make a difference when it comes to what kind of content mathematical AIs can generate? Now, that's a tough question. I myself am skeptical. I feel like similarity-based approaches, like these sort of statistical associations that all these large language models are based on, can always fail in ways that are not robust. So they can always have that one or two examples where it says something incredibly stupid as the output that rule-based reasoner would never do. We can never rule that out. But similarity-based approaches can get closer to rule-based reasoning, and maybe they can get close enough that we can't detect these anomalies anymore if the systems are good enough. It's a good question for just this question of extension. Like, will there be difference in these approaches? And we're sort of seeing it played out in the technology development, which is an interesting thing. I don't take this International Mathematical Olympiad to be very important in that sense, but maybe LLM-based mathematics, like purely LLM-based mathematics, will also reach important results. People have different opinions on that. I feel like we should bet on these hybrid neurosymbolic systems because there is the known rule-based foundation, but not everybody agrees.
I guess one of the other things, I mean, that all sounds right, but is whether or not there's anything that humans are doing that is distinctively different from either of those scenarios, and whether that would be missing from mathematical reasoning if you took it out and just made humans into editors effectively. So the question is whether there's anything in the list or there's anything else that humans doing. I mean, one of the other things humans are doing is that they're not just being trained on a bunch of, a million or 100 million examples of mathematical reasoning as data. They get trained by social interaction with others, right? So from early on, even into expertise, they're constantly interacting with others. They're not just an individual doing it on their own, and the kind of classic example of a thinker, but they're always talking to other mathematicians, they're always talking to their colleagues, they're talking to others, and they're looking at examples of what they're doing, and they're looking at ways in which that influences their own work. So there's something going on there that is distinctive in the way that humans gather information and then use it and produce something creatively and imaginatively, even in the mathematical case, in a way that it doesn't seem that an LLM or call it an LRM or even a hybrid version is going to use. And Markus is a sort of Bodorian, right? So Chomsky, painter, so from that school of linguistics, so he thinks that they've got to have the rule-based system in there as a hybrid system. But there may be other things going on in there that aren't just the statistical, stochastic, parrot type stuff, or the more sort of classical linguistic rules operating on symbolic tokens There's other dimensions in there for humans that might make a difference.
So this is now being discussed in terms of world models a lot. So we want to include some foundational principles into these models. I just saw that there was something like $1 billion investment to LeCun's new project where he wants to develop AI based on world models, which would be trying to capture some of these principles that guide human cognition, capturing those by AI systems. I mean, the most obvious one is embodiment, of course. I mean, embodiment is everywhere when it comes to mathematics, starting from the way we learn mathematics, but also on the level of top-level research mathematicians. People don't often recognize it, but so much of our mathematical work is constrained by our embodiment. I mentioned that the proofs can't be beyond certain limit in length, for example. That's a limit of our embodiment. But of course, the limits of our embodiments are something that humans are really great at turning into strengths. So instead of having these sort of exhaustion type proofs where we just crunch the numbers because we can't do that, we find shortcuts. We try to find as economical way of representing mathematical connections as possible. And the AI systems might not have a similar kind of reason to do that. So I think, yeah, we can model human embodiment in AI systems to a degree in maybe in these sort of world models, or just having a robot that actually needs to function in an embodied way. But of course, we're also then getting rid of the great strength of these systems, which is that we can use the immense computational power behind them. Whenever we turn something into an embodied robot, for example, it slows down incredibly much. So the one solution to get rid of these restrictions is also the solution that sort of gets rid of the advantages. But these world models, I think, are a good idea. They're quite closely related to this neurosymbolic approach without necessarily being committed to certain ideas of linguistics. But that might be something that we can help make the alignment more successful.
One more, Andy?
Thanks, Mark. So that's fantastic. This is not going to be a very clearly structured question, but I think there's a lot of there's an element of human supremacy in terms of talking about reasoning. It has to be in linguistic reasoning, which we know we use. You criticize other systems that don't use it. By that extension, we would eliminate any non-linguistic animals, many capacity to reason, etc., etc., etc. So this element of we're hung up on reasoning because it's smart. By extension, we're smart because we do it, and we still want to make ourselves smarter than the AI. And I wonder whether one of the things we haven't talked on so much is you talked about how not all reasoning is equivalent. And you talk about, is it reasoning because it produces an output that looks like reasoning, or is it reasoning because what's actually doing is reasoning? And you talk about generation of proofs because to make a proof, we assume it involves reasoning, but not all proofs are equivalent. So we know that mathematicians are snotty about proofs if this proof doesn't look clever. And typically, brute force proofs they don't like because that's not clever, because you could do that a simple way to crunch enough numbers. Now, it's interesting that we're almost dismissing brute force proofs, which we know that AI could deliver, because that's not clever. But a brute force proof is actually really robust. So by your own criterion, that's reasoning. It delivered a proof. It's actually super robust because it exhaustively explores space. By that criteria, that's probably a better proof than some dodgy fringe mathematics that some dude put out there. But a mathematician would say, that's not smart because my proof I can put on 2 pages of A4 and it's more efficient in that term because I didn't have to brute force the space. So are we really saying that what we could see is we could see different approaches to generation of proofs coming out of trusting AI and human intelligence? And could the role of a future mathematician be to actually integrate and evaluate those two and put that space together.
Okay, excellent. There's three things I want to say. First of all, I want to say that, yes, these old school rule-based theorem provers, they're sort of maximally robust. But of course, they only do one kind of reasoning, which is just deductive reasoning. And mathematical reasoning is much more than that. We need to have conjectures. We need to know what we want to start proving. We need to generate possible proof steps. So we need abductive reasoning and inductive reasoning in mathematics as well. So for that reason, these systems, even though they're robust, they don't fulfill what we expect from a genuine general reasoning mathematical system. But there's the question, what do we want from mathematics? You mentioned that we like clever proofs, and I think that's exactly right. What do we want out of all this? And this is something that people involved in this DeepMind project, like Terence Tao, for example, has explicitly discussed that ultimately it's still about improving human understanding of mathematics. And I think that's a really important point to remember. Just because we have a lengthy list of theorems that have been proved, it doesn't mean that we have a better understanding of mathematics. So I hope that's going to be the guiding principle, that whatever we generate with AI tools into mathematics, we still have this guiding principle that it increases human understanding of mathematics. Whatever AI knowledge bases, if we can call that, about mathematics is, that can't be the goal. Not with mathematics. I mean, yes, maybe in medicine and things like that, where we have direct applications, but that can't be all mathematics is about. And finally, I wanted to say something about this idea, this human supremacy idea. Of course, one thing that I don't talk about here is that there was a very similar attitude toward non-human animal reasoning for a long time. That because they lack the linguistic ability, surely there can't be anything resembling reasoning. And many people still think like that, coming from this sort of Davidson way of thinking. But at the same time, we've seen that this kind of view has become less and less popular. Now we do associate some forms of maybe simple reasoning with many, many non-human animals. And I think that just shows that this sort of the dangers of hindering progress if we think too much in terms of human exceptionalism. And that's why I dislike the meat chauvinism argument, because it's not a constructive one. It just hinders progress. I don't know whether progress is possible, whether there can be AI reasoning properly, but at the very least, it makes sense to try. And if we assess it thinking in terms of this human exceptionalism, we are not going to get a fair assessment, just like we didn't when we were assessing animal behavior and kept sticking to this old paradigm that there is some sort of automaton.
Thank you.
Thanks.